So if I play this note, for example, this A on the piano, the strings inside the piano, well, not inside this electric piano, don't only vibrate as a whole from one end of the string to the other at 440 vibrations per second, but we also hear secondary vibrations, secondary reverberations, which are generated by the string dividing up on itself. The vibrations traveling from one end of the string to the other, bouncing back on each other, and that divides the string up into various parts.
Right.
So it vibrates as a whole, in 2 halves, in 3/3, as 4/4, and on it goes, creating our overtones. In fact, it's the varying volumes of the different overtones which is what makes different instruments, as well as different voices, sound different, even though they might be playing or singing the same note. So if we play the same note, this A, at 440 Hertz, if we play that on the violin, I'll pluck it, sounds similar because they have the same fundamental frequency. But they sound different because their overtones perform at different volumes. So that's what makes a piano sound like a piano and a violin sound like a violin. And one violin sounds different to another violin as well, as one voice sounds different to another voice. So these secondary vibrations, or overtones, occur at neat multiples of the original vibration. So if we play an A at 110 Hertz, which would be this one, the first multiple of 110, the first overtone, comes in at 220 Hertz. What note is that?
An A.
Another A. Good. And what is the relationship between these two A's? What is the interval between them called?
An octave.
An octave. Good. So this means that when we play this A at 110 Hertz, we are also hearing another A, an octave higher, at 220 Hertz, in its overtones. And that's why playing this A by itself and then playing it together with the next A up sounds pretty much identical to just playing the lower A, if we get them at exactly the right time, that is. That's because there's another element which gives notes their quality, and that's what we call attack in music. The attack is the noise involved in getting the sound going. So if we play these two A's at exactly the same time, we hear one attack and our brains are fooled into thinking that they heard just one note. But with the slightest discrepancy, you can pick up that they're two notes. We can still tell that the notes we hear are the same note or an octave apart, but we hear two attacks. The attack is another element which differentiates different instruments. The sound of a violin and a flute are exceptionally similar if you hear them without the attack. But the attack of a violin, that crunch of the strings, is so distinctive that we are never confused about whether we heard a flute or a violin. So this crunchy sound, just at the beginning of generating the note, that's the attack of a violin. The kind of pingy sound you get at the beginning of a piano note, that's the attack of the piano, and that's part of what allows our brains to differentiate between instruments as well as the varying volumes of the overtones. So in the lower note, the higher one, an octave higher, is already sounding in its overtones. If we play them exactly at once, we might not even notice that two notes are playing, because when we play the lower A, we are already hearing the higher one whether we play it or not. It's there in the A's overtones. So overtones occur at neat multiples of the original frequency. So whenever we play a note, say this B at 30 Hertz, we also generate overtones at 60, 90, 120, 150 Hertz, all multiples of the original frequency. The lower the starting note is, the louder its overtones tend to be, because the overtones reverberate throughout the rest of the instrument. So when we play this low B at 30 Hertz on the piano, we can actually hear very clearly all those secondary vibrations which come from the note, because they make other strings inside the piano vibrate. So you can imagine the perfect fifth waking up inside the piano, vibrating in sympathy, the octave to all that hustle and bustle that comes with that low note. It's just other strings vibrating to the note's overtones. So the electric piano is imitating that. In the overtone.
it's quite clever.
Yeah, it's quite clever. If you open like a real piano, you can see that with the naked eye. So you can see the other notes vibrating. So the first overtone of this B at 30 Hertz is 60 Hertz, vibrates at 60 Hertz. What note is that?
Same B.
And the same B?
Okay, a B.
A B, an octave up, you know? If the string is vibrating at a whole to produce a B at 30 Hertz, how many parts is it vibrating in to produce a B at 60 Hertz?
2.
2, good. The whole string gives us the original note, and the two halves vibrating separately give us the same note an octave higher. How many hertz is our B's second overtone vibrating at? So the overtone caused by the string vibrating in 3 equal parts. So we'll go from 30 to 60 to
90.
90, good. So 90 hertz gives us an F sharp. What is the relationship between B and F sharp? Or rather, what is that interval called? Include B when you count.
So it's B, C, D, E, F. A perfect fifth?
A perfect fifth. So we know it's a perfect fifth, even though this strange sharp has popped up, F sharp, because it's B's second overtone. The second overtone is always a perfect fifth. So generally, we can just count 5 to find the perfect fifth of any note. But B is the only exception. We have to add a sharp. B, C, D, E, F sharp. But generally, we can just count 5. So the perfect fifth of C is
G.
G, good. And the perfect fifth of D?
A.
A. So whilst the perfect fifth of A is E, the perfect fifth of D is A. The mathematical relationship that gives us the perfect fifth multiplying by 1.5 doesn't work both ways like doubling or halving does. It's not that simple or strong a mathematical relationship as the octave, as doubling or halving. So the perfect fifth of A is E, but the perfect fifth of E, what is it?
B.
B. But the perfect fifth of B is
F sharp.
F sharp. So it's not a reciprocal relationship. No. The perfect fifth of A is E, but the perfect fifth of E is B. So we can find the perfect fifth of a note simply by counting up 5, with the exception of B, where we don't get F but F sharp. So if we play A and E together, E and B together, B and F sharp together, we are reminded of why this interval is called a perfect fifth. F sharp, the perfect fifth, falls right in the middle of this first B and the next one up. An octave higher, it vibrates 1.5 times faster than our original B. In the same way, A falls right in the middle of two Ds, because A is a perfect fifth of D. A B falls right between two E's, because B is the perfect fifth of E. So we saw that when we play a note, we are also hearing its overtones at multiples of the fundamental frequency we are playing. These can get picked up and amplified elsewhere on the instrument. If we play this A at 110 Hz, its first overtone sounds at 220 Hz. How many Hz is the second overtone of an A whose fundamental frequency is 110 Hz?
The second overtone, 330.
330, good. So we're not eternally doubling, no, as we might to find octaves, no. To find the note's overtones, we continue multiplying the original frequency, 110, 220, 330, and so on. So what note is that? What note does 330 Hertz give us?
An E.
An E. So we know that because we know the E is the perfect fifth of A, and the perfect fifth appears in the second overtone. So this means that A has a little E in it. When we hear an A, we're also hearing a little E. Okay, so let's keep going. To produce the third overtone, our string or tube of air or reed or whatever would now be vibrating in 4 equal parts, giving us how many hertz? What is 110 times 4?
440.
440. And what note is this?
A B.
Why is it a B?
Because I counted from E before.
So let go of that. Don't try to memorize anything that we are looking at, because it will
440,
interfere.
no, of course, it's double 220.
Exactly. If you hold on to some piece of information, it will interfere in later processes. So everything we look at, just let it go,
Right.
and it won't block your thought process. Of course, it's another
A.
A. And why?
Because it's double 120. 220.
It's double 220, no? So if dividing the original string in half gives us the same note an octave higher, dividing it in half again, so in 4 parts, we'll do the same. We get another A an octave higher than the last one, and 2 octaves higher than our original A, the fundamental frequency that we're playing. So a note is built of more frequencies than just the note we play. But as we see, most of those frequencies are just the same note again. When we play a G, we hear another G, a D, it's perfect fifth, then another G. When we play a B, we hear another B, an octave higher, and then...
F sharp.
Very good. An F sharp, an octave and a half from the original B, and then another B, 2 octaves from the B we're playing. In the first 3 overtones of a note, we find the same note again, twice, and the perfect fifth, which helps underline the importance of that perfect fifth. The perfect fifth gives us the first different note in the overtones of any note, and the only different note in the first 3 overtones. The notes that form a perfect fifth when played consecutively or together give us a sturdy, correct feeling. Depending on musical context, this could make us feel a range of things, but those things will be achieved through the sturdiness and correctness of the perfect fifth. That's the perfect fifth from C to G. Sturdy, correct, harmonious. Maybe the decisiveness of the perfect fifth makes us feel joy or fear. That has to do with the context. But what is without context is that right feeling. The notes sound right and strong, well formed together. And now we understand why. When we play this E, for example, with an A, we are doing little more than bringing out the natural overtones of this A, which we can already hear and expect to hear in the original A. So everything feels right with the world when we do that. So the interval between an A and an E sounds right simply because it's what is. When we play this interval, we are simply reproducing the nature and behavior of the physical world, and the proof is in the word. We have perfect octaves and perfect fifths, and perfect literally means, if we look at the etymology, by fact, per fact, perfect. Just how person meant per sound, perfect means per fact, by fact, what is. What is what we find in the natural overtone series. Now, if we take that E down a half step, we find another fifth. So if we play A to E flat, taking the E down a half step, it's still a fifth because we count 5 from A to E flat, but this one sounds anything but right. It's a more complicated sounding interval, even without context, tending towards the dark and unknown or uncomfortable. And that's because, even though we're playing this interval with no musical context now, the context we play it in is the very physical world, the physical medium in which we are surrounded by perfect fifths occurring naturally. So instead of playing A and E, we play A and E flat. We find that suddenly everything sounds very off. We are alluding to the perfect relationship between A and E, but we have altered it. The sensation of or meaning of the interval becomes more complicated, more faceted. It could mean anything from dread to anticipation to guilty ecstasy, depending on the context. It's no longer simple, correct, sturdy, right and familiar. It's no longer a simple reflection of the way things are, perfect, by fact, of the way the reverberations naturally occur in the Overtone series. No. It's something else, far more complicated now. It might be dangerous, it might be pleasurable. What it's not is simple. So notes are named A to G, giving us 7 notes. And then we have a further 5 divisions which we mark with sharps and flats, which gives us a total of 12 distinct frequencies before we get to cloning them by doubling and halving. But as we are seeing, it is not so much the frequencies or notes in themselves which are important in musical communication, but rather the relationships between those notes, which we call
the overtones.
The relationships between the notes, which we also find in the overtones. What are those called? What is a perfect fifth an example of? A perfect fifth is a type of
interval,
of which so far we've named 2. So what was the relationship between these 2 notes? Between this A and the next A?
The interval is an octave.
An octave, good. Or more correctly, a perfect octave. It is perfect or by fact because the interval just reproduces what happens in the first natural overtone of any note. And it's an octave because we count 8 going from A to A. So whenever we play a note and then the next note up or down of the same name, we have a perfect sounding ascending or descending octave. So what was this interval called? The one between A and E. If we forget, we can simply count from A to E to be reminded.
And it's a fifth, perfect fifth.
A perfect fifth. Good. So the interval between A and E is called a perfect fifth. The notes belong together because they are factually together. Out there in the vibrations of the physical world, they are together. When we play A and E flat rather than A and E, we still have a fifth. We still count 5 from A to E flat. No, but it's no longer perfect. It's not by fact, and it's not the fifth we find in the Overtone series. It's been modified. The notes do not blend together perfectly anymore, or anything like perfectly. Now we have what we call a diminished fifth. So this interval is called a diminished fifth. The E flat is reducing the size of the perfect fifth interval, diminishing it. So now we know the names of 3 intervals. If we go from A to A or G to G, it's called
an octave.
An octave, or a perfect octave. And if we go from A to E or C to G,
a perfect fifth.
A perfect fifth. Fifth because we count 5 from C to G, C, D, E, F, G, and perfect because of the sturdy factual sensation it imparts. But C to G flat would be what interval?
A not so perfect fifth, a diminished fifth.
Very good, a diminished fifth. And the diminished fifth is named so because we have decreased or diminished the perfect fifth by a half step. A half step is the distance from G to G flat. So, musical terminology is suggesting to us that we are not hearing the diminished fifth as an interval in its own right, per se, but rather as a bastardization of another interval, of the perfect interval. This goes a long way to helping explain why the diminished fifth sounds so uncomfortable or tense to us. In most countries, it's the interval used for an ambulance siren. The disturbance of perfection makes us all the more aware of that perfection. The diminished fifth makes us aware of the absence of the perfect fifth. The diminished fifth, taking us so close to that special place of harmony, the strongest harmony that any 2 different notes can share, makes us want to return to that safe, familiar space and creates apparently unbearable musical tension. The diminished fifth interval was even banned in some types of church music. Donned the tonus diabolicus, the diabolic tone, it was thought to be entirely unholy and thus unmusical. The power in that interval lies in how it violates perfection by faction. the way things are, while still alluding to it, whilst bringing us close enough to it to remember that the clean, simple, perfect fifth is everything the messy, dissonant, diminished fifth isn't. And of course, the visceral reaction we have to experience in that, which convinced enough people to not reproduce this particular interval in their music and even punish those who did. Fascinatingly, the relationship between the perfect and diminished fifth is suspiciously similar to some stories of God and the devil, or good and evil. The devil is often understood as a fallen angel, and what is a fallen angel but broken perfection? Could the devil really be the metaphor of a broken perfect fifth, of the tonus diabolicus, and God a metaphor for the perfect fifth? Quite possibly. The godly number according to the Bible is 7. In some cultures, this is represented as 3 sevens, and there are 3 perfect intervals in music. What is the diabolical or evil number, which also appears repeated thrice in popular culture too, giving us the 3-digit number
666, the number of the beast.
666. If we count in half notes or half steps, the smallest interval we recognise, there are 7 half steps in the godly perfect fifth, and there are 6 in the diabolical diminished fifth. There are precisely 3 perfect or diminished intervals in music, which may explain why we get 666 and 777. So tonal systems in all musics, even though our focus in this course is on what we have come to call Western music, are very much a reflection of the natural physical world rather than some artificial system we invented for music. There really is something transcendental about musical intervals, not only in how we experience them, but also in how the patterns we find in them are the same as those we'll observe in anything from geology to religious law.